to my talk, my greenhouse talk, everyone. My name is Kaan Genç. Uh, I'm a PhD student at The Ohio State University, and I'm also an intern at Dendron right now. So my research at my PhD research, one part of it involves data races, which I want to talk about it today because I think it's a very important topic. During my talk, please feel free to interrupt me if you have any questions. So before we can talk about data races, it's important to talk about concurrency. We need to understand what concurrency is, because these are a type of concurrency bug. So modern hardware now has lots and lots of cores. For example, this is a picture of a relatively new Intel processor, which has 4 cores. My computer has 8 cores. My phone has 6 cores, I think. Most modern processors nowadays, even tiny, small embedded ones, have multiple cores. And the key thing is, when we write our programs and we run our program, it's only going to take advantage of a single core, because that's kind of the baseline. That's how programs run. And if you want to take advantage of multiple cores of the processor, we need to use multi-threading to create new threads that then take these cores and then run on those cores, which allows us to take advantage of multiple cores. For example, here I did a little benchmark checking how long it takes for a parallel compression program to compress about 5 megabytes of data. And so if you look at the chart and you look at the left side, with a single thread, it takes about 45 seconds. But if I increase the number of threads, it goes down, around 8 threads. It's already down to 10 seconds, and there's very minor improvement after that. But that's still an incredible difference, right? By enabling multi-threading and using more threads, that's about a 4 times speed up. So it's very important with modern hardware that we use multi-threading and we take advantage of the additional cores that these modern processors have.
Hey, one thing that I've always wondered, and I feel like there's a easy relationship, but what between a core and a thread? Like, I don't think you have 16 cores to have 16 threads, right? What's the relationship?
So there's a little confusion on the terminology there, because the people introduce different terms. So a lot of processors now have a feature called hyperthreading, where they can use a single CPU core to run 2 threads at the same time. And how it does it is that a lot of times, there are things that will block a processor from running, that will block a core from running specifically. And whenever something like that happens, it just swaps out the other thread so that the other thread can run. So, it's constantly swapping between these 2 threads at a hardware level, which is a lot faster than what something like an operating system can do. So that allows it to run with almost perfect performance. It allows a single core to run 2 threads on it.
Ah,
So
cool.
yeah, so that is becoming pretty common, I think. Yeah, so for example, my computer has 8 cores, and then it has hyperthreading, which gives me 16 threads running in parallel.
I remember that. I think it was like the AMD Ryzen. I used to have I think the same thing. Maybe I had a 4-core and it was 8 threads. Interesting. Okay,
Yeah,
got
yeah.
it.
Intel processors also have it. I think it's only like AMD sorry, not AMD, the ARM processors, like the mobile phones, that don't have it, I think. I'm not sure.
Oh, okay. So it's 1-to-1 on like on an iPhone or Android.
I think so. I think so.
Okay.
But
Cool.
those platforms have different concerns, where they have they have like asymmetrical cores where they have some cores that are more powerful and some cores that are less powerful. They have different challenges. So multi-threading is great. It speeds up our programs and it's very important that we use it. But when we use multi-threading, it causes or it opens up our programs to new kinds of bugs. And one of the most important bugs, in my opinion, that you can see are called data races. So now I want to talk a little about what data races are, what do they look like, what kind of problems they can cause. So what a data race is, so it's concurrent accesses by different threads that access the same data at the same time that are conflicting with each other. So rather than giving you this formal definition, I think a good way to explain it is you can imagine this. You have two threads, and then the key thing with multi-threading is that these threads share memory, so they can access the same memory. And so you have two threads, they're running at the same time, and they're both trying to access the same variable. And imagine that both of them are trying to write into that variable. One of them is writing 0, the other one is writing 10. What's going to happen there? Which one? Normally in a program, when you write, if you say x equals 0, after that point, x is going to be 0. But now that we have multi-threading and we have these threads accessing the variable at the same time, you set x to 0, but then x isn't 0 anymore. Another thread comes and changes it to something else. Or while it's running at the same time, both of them are trying to write into it at the same time. These can cause some issues, which we're going to see in a moment. So here I have a small example. So imagine that you write a program, and in your program you create two threads and you run them at the same time. And these threads are doing these. So you have one thread that goes and does some heavy calculations and then writes the results into the variable x. And then it writes 1 to the variable y. And then your other thread, it checks if y is equal to 1. If it is, it prints out the results of x. And imagine that initially x and y, these variables are set to 0. So the question here is, can this program print 0? So under normal circumstances, if you think about it, if this was a typical code without multi-threading, if we run this, well, we write to x, then we write to y, then we check if y was written, then we print x. So there isn't really a way that we would be able to print 0, right? Because we do the calculation, then we write to y. So we check y. If it wasn't 1, that doesn't seem like that could be possible. I'll give everyone a second here. I'll pause and give everyone a second here to think about this example a little bit. Can you imagine a way where this code would break in some way that this would cause issues? This multi-threading?
What's tripping me up when I'm trying to think of this is that I feel like that x equals power 2 to 32 will just take a really long time to calculate.
Mm-hmm.
So we'll never get to y equals 1. And if you don't get to y equals 1, then thread 2 won't run.
So it won't take that long. I can promise you that. I mean, one thing is that power 2 to the power of 32 is it's a big calculation, but it's not that big. And another thing
No,
is
I
just
think
that.
that one is just a bit shift. I guess it's just a bit shift too.
Yeah, right. That's what I was about to say.
It's
So
just a bit shift, so
right.
it's not going to be. But you see, I don't know. It feels like you have to do a register. You have to do a calculation plus a register assign before you even do the if check. for the program to print 0.
Hmm.
It seems possible, but unlikely. Like, I guess it's indeterminate,
Hmm.
right?
Right. So yeah, that's one of the issues. So the key thing here, though, is that if this program, if you went into assembly, wrote this in a very basic way, and you ran it in an old computer or something, a very old processor, maybe it will run correctly. But at least with modern hardware and modern compilers, we have an issue. So compilers are allowed to move things around. That's a very key thing for optimizations because it allows, very basically, it allows things to be more optimal. So for example, maybe the compiler might decide, this calculation here, that's going to take a long time. Maybe I can set the variable y a little earlier to save on memory bandwidth or something. Maybe the compiler figures out that moving the y equals 1 up is somehow more performant, and the compiler is allowed to do that. So if the compiler moves that up, then we have an issue because in that case, we set y to 1, and then we start doing this, heavy calculation where we're doing x equals something, and we're waiting for that calculation. Thread 2 might go ahead and check, is y equal to 1? And it is, in which case thread 2 prints x, which is 0 at this point because we haven't finished our calculation yet. So we just end up printing 0. So as you can see, that's the dangerous thing, which is that if this code were to run without multi-threading, if it were running line by line, this bug could have never happened. And even with multi-threading, if you were just thinking about it, you wouldn't see this bug because you first set x, then you set y, and you wouldn't have any reason to suspect why it wouldn't happen in that way, because that's how we're used to our programs running. But in reality, because of compiler optimizations and processor optimizations, it doesn't actually happen that way. Things can change. And so I want to show there are tons of different bugs that can happen, but in the interest of time, I want to show just one more example here, which is called out of thin air values, which is incredibly crazy in my opinion. So again, we have two threads running some code, and again, assume that x and y are initially 0. Is there any chance when we run these threads and just this code, nothing else, is there any chance that we can end up with x and y being equal to 42 or anything other than 0?
Man, I know the answer is yes, but I'm struggling to figure out how.
Right, right. Yeah, I wouldn't be asking it
Ah,
otherwise.
I know. Wait, I want like 10 more seconds.
Yeah, that's fine.
I mean, is there something crazy that happens with a double equal to operation where it like
No,
sets the
no,
value? No, right?
no.
Okay.
Okay.
I don't know if anyone else on the call has
It's
figured it out,
it's hard.
but
You wouldn't be able to figure. I mean, I'm being a little I don't know what the right word for it is, but you wouldn't be able to
tricky.
figure this out. Yeah, you wouldn't be able to figure this out without knowing the trick to it. So there are two issues, and there are two things happening here for that result to happen. One is that compilers are allowed to replace assignments with literal values. They're allowed to replace variables with values. So here, in the code, we have x, we check if x equals 42. And then after that, we had y equal x. So at that point, because we checked it, we know that X is the number 42. And so the compiler is actually allowed to replace the variable X with the number 42. Same on the other side. We checked Y is equal to 42. We know that Y is 42. So the compiler can go ahead and replace the variable Y with 42. There are some situations where this might be more optimal to do, and compilers are allowed to do this. Um, so the second issue comes with a feature of processors called speculation. So whenever you hit a branch in a program, a branch is something like an if or a switch, or like the condition in a for or while loop. Whenever you hit any of those, the processor has to stop and wait for some results to be ready. If you hit an if, when you hit if x equal 42, the processor has to stop and wait to figure out if x is equal to 42 or not, which takes a while actually. And then after it can only continue after it makes that decision, which is actually kind of slow. So what processor designers did is they implemented this feature where the processor will just guess what the outcome is going to be. So it'll see if x equal 42, it'll say, you know what, I think this is going to be true. And then it'll start executing. And this is actually safe because what happens is it later checks if the outcome of that branch was true. It'll check if it guessed correctly. If it did, everything is great. The processor can continue running and you lost, no performance. If it guessed incorrectly, then the processor throws away, whatever work that it did, goes back and then continues from the other side of the branch. And this still ends up being a lot more optimal than just waiting. So what can happen in this example is that the processor might start speculating when it's running this code, and it might start speculating that what, this if the branch of this if is going to be true. And then because it guessed that, it goes ahead and writes the number 42 into the variable y, which is, again, this is safe as long as we come back and then throw away whatever work we did once we have the outcome of the branch. But while one of our threads is doing this, we have another thread running at the same time. That thread goes and checks what the value of y is. It checks if it's 42. And the thing is, it is 42 now, because our first thread, while doing the speculation, it actually made a write. So thread 2 sees this value here and sees that this if is true, and then goes ahead and writes the number 42 into the variable x. So it goes and writes the variable value 42 into the variable x. And then because it wrote 42 into x, the speculation that our first thread did when it was checking is x the number 42, that comes true now because thread 2 wrote that value. So because that speculation is now true, the speculation is true, thread 1 doesn't have to throw away all of its work, and so everything can continue running. So suddenly, it pulled out a number 42 out of nowhere.
That's absolutely wild.
It's
I think,
incredible.
wasn't there a bug with speculative rights? Like, wasn't that's what caused an issue a few years ago?
Yeah, it's not this issue. I'm not sure if this exact issue has been replicated in practice. I think
Yeah.
out of thin air values are a little more a theoretical issue. We know this could happen. I don't know if anyone has like an example of, hey, run this code and you see out of thin air values.
No, it's beautiful. It's one of those things where like every step was logical, like to do it for the optimization, but at the end the
Right,
result is not what
right.
you
That,
expect.
that that's
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 very
the big,
cool.
right. That's the big issue. So, and for just for an example, both of these programs could be made correct. So in order to fix data races, you have to use locks or atomic operations. So with the first program, one way, there are multiple ways you can implement this, of course, but one way you could do it is you could set and get the variables y with atomic operations, which prevents things from moving around and makes sure that everything executes in the order that you want. So this is not in any particular language, of course. I'm just writing pseudocode. And then with locks, again, that's another option. You can acquire and release locks. And locks enforce mutual exclusion, which means that only one thread can hold the lock at a time. So with the other example, if we had locks around these, only one thread would be able to enter that block, run the code inside it, and then leave. And the other thread has to wait for the first one. So the the fixes to these problems aren't hard, but what's hard is understanding the problem and figuring out where it's happening. So that's really hard. So yeah, like I said, data races are really hard because of several issues. One is that data races will often occur only in some executions of your program. So you run your program once, you see a bug, you run it again, the bug disappears. That makes it really hard to figure them out. And that's because, small changes in timing can affect whether the data race happens or not. If something is a little delayed, maybe the accesses won't conflict and then you won't see the data race. And so because it's unreliable like that, if you want to reliably reproduce data races, you need to use record and replay systems. So we have these systems that can record the execution of a program, and then when you rerun your program, it makes it run in the exact same order. So if there was a data race, you get that exact data race in the second run. So these are great, but they impact performance. And what that means is, you can't just put this record and replay system on a user's machine, for example, because that's going to be slowing down your program. And because you can't put it in the user's machine, if they have a bug and they send you a bug report, you don't really know how you can reproduce that bug if it's a data race. And finally, diagnosing data races is really hard because if you try to add prints into your code, or you compile in debug mode, or you attach a debugger, all of this can change whether the race happens or not. It can hide the race. A lot of print functions, for example, have locks inside them. So if you use the function print, suddenly you're adding locks into your program actually, and that's going to hide the race. Or if you're compiling in debug mode, maybe the compiler is not going to do those optimizations, and so the race won't happen. So that means it is really hard to figure out if you do have a race. So that brings me to my next topic, which is how we detect data races. So data races is hard, they're dangerous. How do we find them then? Well, we have lots and lots of different methods of finding data races, thankfully. So I couldn't possibly talk about all of these methods. I'm just going to look at two of them. So one very simple method is called log set analysis. And what it does is that it checks if whenever you're accessing some shared memory, if you are holding the same logs as the previous times you accessed it. So again, imagine that you have two threads. They're both executing some code. They're acquiring and releasing this lock m. So what it does, it gets the lock, accesses the variable x, releases the lock, and then accesses the variable y. And then our other thread, it gets the lock m, accesses x and y, and then releases the lock. So you can see here very easily that on the left, we were holding the lock m when we access the variable y. On the right side, we weren't holding the log m when we access the variable y. So the log set analysis will just say, hey, this this access to Y, there might be a race. So this is a very simple way to find data races. But the problem is that this is actually very prone to false alarms. So here I have the same example changed slightly, very slightly. And the change here is that if X wasn't Y, the program would have exited, and then we wouldn't run print Y. With that small change, since we're again accessing Y without holding the lock set analysis would just say, hey, there might be a race there. But actually, there is no data race in this program. If anything happened where it might race, the program would have actually exited already. But lock set analysis will still report this. So there are a lot of ways to improve this. One method that does have a lot better results is partial order analysis. And the most famous one is called happens before analysis. So this is very widely used in practice. So we have, and most commonly, we have thread sanitizer, which has been built into GCC and CLang, the biggest two, C and C++, and I mean CLang, it integrates with a lot of other compilers. So these are the biggest compiler architectures right now. So it's integrated into all of them. And the way it works is whenever you have acquire and release operations on the same lock, it says that these are ordered to each other. So here, in this example, we have one thread that's acquiring and releasing lock M, the other thread acquires and releases lock M, and then this analysis would say, okay, these are ordered to each other. And whenever you have conflicting accesses, for example, when we're accessing the variable y on the left and on the right, it just checks, okay, are these accesses ordered to each other? And we can see that they are, right? So we had the y release, there's an order, and then we have the acquire, some other stuff, and then print y. So they're ordered to each other through that release to acquire ordering. There is no data race. So partial order analyses are very accurate, but the problem with them is that they can sometimes miss data races. So here I made a very small change to the program, which is that instead of exiting when I see that, instead of exiting when I see that, instead of reading X and then exiting if it's not one, I have my second thread is setting X to 2. So first one sets X to 1, Y to 1. Second one sets X to 2, then prints Y. In this case, there is a data race in this program, but partial order analysis will actually just miss this because it just sees that there are locks, says they're ordered, says there's, and then it just thinks there's no data race. And just to plug myself here, I actually have a paper called Dependence Aware Unbounded Sound Predictive Race Detection, which has been published around 2 years ago now, which actually addresses this case at least, and several others, so which improves the data race detection capabilities of partial order analyses. So, like I said, there's a lot of different methods for detecting data races. I couldn't possibly cover all of them, but please feel free to investigate if you're interested, or you can message me after this, or yeah. So you're a programmer, you're writing a program. What do? You want to protect yourself against data races. Well, if you're using a language like Python or JavaScript, there's nothing you have to do. These languages don't really have shared memory parallelism, which means you can't have multiple threads running at the same time, accessing the same memory. There's nothing for you to worry about. But if you do use languages like C, C++, Java, C#, Go, Rust, I think in some cases, maybe with unsafe code, with a lot of these other languages, you do have to worry about this. A few things you can do. You can use data race detection tools during testing. So two most common ones. We have thread sanitizer, like I said, built into most compilers now. There's also RV Predict, another good program. So what you can do is you can set up your testing suite to run these tools and check if there are any data races. And if you have a very comprehensive testing suite that replicates what the program looks like in the real world, this is going to find a lot of data races and allow you to fix things before they happen. Another option is that you can look at record and replay systems. There's a great project called the RR project, which is a very efficient and very powerful record and replay tool. I would definitely recommend checking it out. And another option is that you can consider an in-production race detector. So the one that I know about is called RaceMob, which it's meant for in-production systems. You put it in your program. Normally, a regular data race detection analysis would slow down your program a lot. But this only slows your program down very slightly, which is acceptable in production, and then uses the results from lots of hundreds and thousands of users, or if you have hundreds of servers, it uses the results from all of those to figure out where data races are happening. So that's about all. Did anyone have any questions? I'm happy to answer any questions.
Hey man, first of all, this was extremely informative. It was very like it's been a long time since I've thought about data races, especially since a lot of our tooling and what I've worked with recently is Python and JavaScript. Um, but it is pretty cool to see. And theoretically, it's very straightforward. But it like in practice, it seems so complex to be able to do this, to be able to debug. Um, in the in-production race detector, I'm assuming it takes a high level of investment to like set up that many systems. Is it kind of, is that right? Or are there like pretty straightforward ways of running the same code in like so many environments and finding which environments cause races?
It's so the thing with data race detectors like these partial order analyses is that they will detect data races even if they don't happen exactly. Like I said,
Yeah.
whether a bug actually happens or not, that depends on very critical, small timing differences. But the way that these these data race detectors work, you know, they're checking this ordering, and they can actually find a lot of data races that didn't necessarily happen, that you didn't see the bad effects of the data race, but the race was there. They can find all of those.
Oh,
So it's
but this is,
and
I thought,
sorry, go ahead.
my understanding was this is static code analysis, right?
Oh no, this is dynamic. So sorry, yeah, I should have
Oh, okay.
mentioned that. So my personal expertise is more with dynamic analysis. So I didn't
Yeah,
even try to talk about the static analysis tools, because there's tons and tons of dynamic analysis methods, tons of static analysis
I
methods.
see. Okay, okay. No, that's good to know. Because then I see how this is very related to that option 3, where you're basically running the same code with different timing and intervals to catch potential issues.
Hmm.
Very cool.
Yeah, and since especially with thread sanitizer now being built into compilers, it's very easy to use. You just pass a flag to your compiler, and then it starts finding data races. So it's very convenient, and it's very useful now.
Well, I'd say if no one else has questions, we're lucky to have you in our community because we can ask more questions about
Yeah,
data
yeah, absolutely.
races in the future. Um, so I'd say we can call this a wrap. Thanks a lot, Khan.
Yeah, thank you very
Thank
much
you.
too.
Those examples were pretty cool thought exercises.
Yeah.
Yeah. All right. Bye all.
Thank you.